Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. In this video we're going to be looking at a sequential circuit element called a flip-flop, and this particular flip-flop is called a D flip-flop. It is often called a transparent flip-flop because whatever value it has at the clock transition is transferred over to the output. So it basically passes the input over to the output. We're going to take a look at just the diagram for it, the block diagram, the circuit symbol, if you will, and we're going to look at a little simulation of it on MultiSim Live. Okay, let's get started. So we are looking at a D flip-flop. I don't like those T's. Flip, flop. Okay, great. And so a D flip-flop, or any flip-flop, it's going to store one bit of information. All right, it's controlled by a clock. And it changes on a clock transition. A clock transition can be from 0 to 1 logic level, or 1 to 0 logic level. If it goes from 0 to 1, this is called a positive edge. If it goes from 1 to 0, it's called a negative edge. And so if I have a clock signal, that looks like this, okay? So we have edges that are going from 0 logic level to 1 logic level right here, right here, and right here. Those are all positive edges. And then we have the edges that are going from 1 to 0. These are all the negative edges. So the D flip-flop, which again stores a bit of information, is going to change what it's storing on one of these edges depending on what type it is. And so the most, well, I don't know, I guess the easier type to understand for me are the positive edge ones. And so we'll take a look at that one and its diagram. So here is a D flip-flop, D, and it's going to have a clock. It's going to have an output Q and an inverted output Q bar. So this is the output. This is the inverted output. This is the input, and this is the clock. So this is positive edge triggered because, first off, this triangle means edge, and then because there's no bubble means positive. All right, so we could have a situation where that looked like this. This would be a negative edge. Okay. So that triangle represents that it's an edge trigger. The no bubble here says it's a positive edge, so this is a positive edge triggered D flip-flop, and that means it transitions on these blue edges for the clock that's coming in. All right, one more thing I want to show you, and then we'll go to a simulation, is basically the function table here. So we have values of Q, but there's a time element now. And so, as we go along, we're going to hit a transition, and so Q can update at that point, and then Q can update at that point, and Q can update at that point. So we can say this is like Q, this one would be Q at time plus 1, and then this one would be at Q at time plus 2 on each of these transitions. So we're looking at what happens at Q of time plus 1, referencing the previous Q. And so there's always one greater than the previous one, right? So if I have a D that's 0, what is Q going to be, the next Q going to be? It's going to be 0. And we call this functionality set. Sorry, not set. We call this functionality reset. So this would be a reset. That's the operation. And if I have a 1, then the output is a 1, and we call this a set. So this is what we mean by it being a transparent flip-flop, is that the output is simply going to be the input. And if it's a 0, we reset the value to 0, and if it's a 1, we set the value to 1. And that's it. So that's the functionality, how the behavior of the D flip-flop goes. And let's take a look at it in action. So I've gone ahead and built up this circuit, and so you can see right here we have the D flip-flop, we have the D input, and I have a digital constant attached to that I can change from logical value 1 to 0 and back. I have a 1 Hertz clock, so we can see this happening in real time, and the clock is a positive edge triggered clock, so we should see changes in the value of Q based on the positive edge. Don't worry about the set and reset, we can get to that in a later video, but I do want to look at the output Q. We are measuring its value here with this probe V that's green. And this probe V that's blue is the clock. Now typically these would have the same voltage values, but for us to see this more clearly, I changed their voltage values. The clock is at 3.3 and the output is at 5, so they're different logical systems, but that's okay. So what I want you to look for when we look at this graph is that the green, which is the output, only changes when there is a positive edge on the clock. And you can already see one of those right here, but let's get it started. And so here we can see the clock changing. And we see that on this positive edge, the output Q turned into the input D, which was a 1, right? And so there we see that happening. Now if I change the input to 0, and so then it changes here again on the positive edge of the clock. If I change it back to 1, and then to 0, to 1, and to 0, so it only changes on the positive edge of the clock. And it's equal to the value that I set it at. So hopefully that's pretty clear to you looking at that graph, well, I hope you get an idea of what the D flip-flop does and how it stores a value, how it changes its value, and how it utilizes the clock, what a positive and negative edge clock trigger is. That's all we have for today. Thanks again for watching. My name is Mike Stanzik, and this is Digital Electronics Classroom. Have a wonderful day.